Please subscribe to support the channel. What if a star was moving so fast, so violently, that it could tear itself away from its home galaxy, escaping not just the gravitational grasp of billions of stars, planets, and black holes, but flying endlessly into the cold, dark void between galaxies? The very idea sounds like science fiction, a kind of celestial missile shooting through space with unimaginable power. But this is not fiction. It's real. These stellar outlaws exist, and they are known as hypervelocity stars. Among the vast wonders of the universe, supernovas exploding with more brilliance than entire galaxies, quasars radiating cosmic energy, and black holes devouring matter at the edges of space-time, hypervelocity stars stand out because of their sheer defiance of galactic boundaries. They are the escape artists of the cosmos, capable of breaking free from something as enormous as the Milky Way itself. Think about that for a moment. Our galaxy is made of over 200 billion stars, all gravitationally bound together, yet some rare stars are powerful and fast enough to punch through that binding force and fling themselves into the intergalactic wilderness. Now, why should we care about them? Because they're not just fast, they're dangerous. Imagine a massive, blazing star hurtling at thousands of kilometers per second, indifferent to anything in its path. These aren't objects we can just ignore. Their sheer kinetic energy makes them cosmic projectiles with the potential to alter entire planetary systems if they ever pass close by. They carry the same unpredictability and threat as a stray bullet, but on an astronomical scale. And what makes them even more fascinating is their rarity. Hypervelocity stars aren't sprinkled everywhere in the night sky. They are rare jewels hidden within the fabric of our galaxy and beyond, each one telling us a story about the violence of black holes, the chaos of colliding galaxies, and the fragile dance of binary star systems. Each discovery of such a star peels back another layer of cosmic mystery, offering astronomers not just awe, but valuable clues about how galaxies evolve, how black holes interact with matter, and how gravitational forces shape the universe itself. So, as we embark on this journey, we're going to unravel the story of these wandering suns piece by piece, from what defines them, to how they're formed, to what terrifying consequences they might bring if one came too close to Earth. Every segment of this discussion will peel back a different facet of their strange existence. This is not just a story of speed, it's a story of survival, violence, and exile on a cosmic scale. We've established the intrigue, the drama, and the cosmic danger these wandering suns represent. Now, let's take that curiosity one step further and ground it in a clear definition. Because before we can understand why hypervelocity stars matter, or why they're so extraordinary, we need to understand exactly what they are. A hypervelocity star, at its simplest, is a star traveling so fast that it can escape the gravitational grip of its host galaxy. To put that in perspective, most stars are bound by the gravity of their galaxy in the same way that planets are bound by the gravity of their star. Just like Earth orbits the Sun without flying away into interstellar space, stars within the Milky Way orbit its center, caught in the pull of its immense gravitational well. For the vast majority of stars, this relationship is permanent. They're trapped forever within the galactic family, endlessly circling around the core for billions of years. But hypervelocity stars are different. They're the cosmic exceptions, the renegades that manage to exceed the escape velocity of their entire galaxy. And this isn't just a small difference in speed, it's a radical leap. Think of galaxies as enormous cosmic prisons of gravity, their walls impossibly high. Most stars never even come close to climbing out of these walls, yet hypervelocity stars don't just climb them, they leap over them. Now, to put this into context, let's think about how speed and gravity interact on smaller scales. On Earth, we're familiar with the concept of escape velocity, the speed an object must reach to break free of Earth's gravity without falling back down. For Earth, that velocity is about 11.2 kilometers per second. If you throw a ball in the air, it doesn't escape. Gravity pulls it back. But if you launched it at 11.2 kilometers per second or faster, it would break free of Earth forever and head out into space. The same principle applies to galaxies. For the Milky Way, the escape velocity is roughly 550 kilometers per second, 50 times Earth's escape velocity. That means that any star wishing to leave our galaxy forever needs to exceed that incredible speed. And hypervelocity stars, they don't just exceed it, they obliterate it, often reaching speeds well over 1,000 kilometers per second, and in some cases, even surpassing 1,700 kilometers per second. But what makes this definition even more awe-inspiring is the sheer rarity of these stars. They're not a common phenomenon. Out of the billions upon billions of stars bound to their galaxies, only a handful ever gained the conditions necessary to be launched outward at such velocities. Imagine looking at a massive crowd, say a stadium with 200,000 people, and then imagine one person suddenly sprinting out of the stadium so fast they could outrun a jet. That's essentially what a hypervelocity star is doing on a galactic scale. It's important to distinguish here that hypervelocity stars are not the same as ordinary fast stars. Many stars move quickly. For instance, so-called runaway stars can speed through the galaxy due to past interactions or explosions, but they're still tethered to the galaxy's gravity. Hypervelocity stars go beyond that. They are the true escapees, breaking every chain and flying into the uncharted spaces between galaxies. We'll talk more about this difference later, but the definition makes clear that hypervelocity stars are in a class of their own. What also makes their definition interesting is that we don't just classify them by their speed alone. Their trajectories are equally important. Astronomers can trace their movement across the galaxy and determine whether a star is merely speeding along in orbit or truly leaving the galaxy behind. It's not enough for a star to be fast. It must be fast in the right direction. A star moving quickly but circling around the Milky Way's core is still bound to it. But a star streaking outward, climbing away from the galactic plane, and showing no sign of being pulled back, that's a hypervelocity star in action. Let's pause and reflect on just how strange this definition really is. A star is not some small rock or comet that can easily be flung around. Stars are massive, often tens to hundreds of times more massive than our sun. To accelerate something that huge to such extreme speeds requires unimaginably powerful forces. We're talking about gravitational interactions with supermassive black holes, violent stellar explosions, and even the cataclysms of colliding galaxies. The fact that we've even found such stars tells us the universe is far more violent and dynamic than the peaceful night sky suggests. And here's another layer to their definition. Hypervelocity stars are not permanent members of any galactic system once they're ejected. They become wanderers, drifting through the vast void of intergalactic space. For billions of years, they may travel alone, leaving behind their siblings, their star clusters, and their galactic homes. They embody exile and loneliness at the most profound scale, a single star carrying the light of its nuclear fire across cosmic darkness with no companions but the cold vacuum. So when we define hypervelocity stars, we're not just identifying a class of fast-moving stellar objects. We're pointing at one of the rarest, most violent, and most extreme outcomes of astrophysical processes. They're messengers of galactic dynamics, physical proof that the cosmos is not static, but explosive, full of forces powerful enough to fling suns like stones from a slingshot. We now know what hypervelocity stars are. Rare cosmic escapees that can outrun the gravitational chains of their galaxies. But to truly appreciate just how extraordinary their motion is, we need to zoom in on the raw numbers, the speeds themselves. Because numbers without context are just abstractions. But once we compare them to everyday experiences, to the speeds of planets, rockets, and even ordinary stars, the reality of hypervelocity stars becomes staggering. Let's start with something familiar. Earth. Our planet orbits the sun at about 30 kilometers per second. That's roughly 108,000 kilometers per hour. Already, this is a speed that boggles the human mind. No human-made machine comes anywhere close to it on a sustained basis. Yet to the universe, Earth is moving along at what you might call a casual stroll. Now, consider our sun itself. The sun isn't just sitting still. It's orbiting around the center of the Milky Way. Like other stars bound to the galaxy, it travels at about 220 kilometers per second, which translates to nearly 800,000 kilometers per hour. That's fast enough to circle Earth in less than 3 minutes. To us, this seems unimaginably fast. And yet, it is the average galactic cruising speed, a normal pace for a star bound by the Milky Way's gravity. But now let's step into the realm of hypervelocity stars. These stellar outliers break the mold completely. Instead of hundreds of kilometers per second, they can blaze through space at 1,000 kilometers per second or more. That's about 3.6 million kilometers per hour. To put that in perspective, at that speed, a hypervelocity star could travel from Earth to the Moon in less than 6 minutes. And some of these stars go even faster. The record holders reach speeds of 1,700 kilometers per second, which is over 6 million kilometers per hour. At that velocity, one of these stars could circle Earth's equator in just under 7 seconds. Let's compare further to the fastest things humans have ever built. The Parker Solar Probe, the fastest spacecraft to date, has reached speeds of about 700,000 kilometers per hour as it slingshots close to the Sun. This is humanity's crowning achievement in terms of speed, and yet it would appear sluggish compared to a hypervelocity star. These stars move at least 5 to 10 times faster than our most advanced probes, and unlike spacecraft, they're not powered by engines or technology. They're driven solely by gravity in violent cosmic interactions. To stretch the comparison even more, think about bullets. A high-speed rifle bullet travels at around 1,200 meters per second, just over 4,000 kilometers per hour. That's fast by human standards, but hypervelocity stars laugh at that figure. They move at speeds nearly 1,000 times faster than a bullet. Imagine a bullet that doesn't just pierce through air, but through galaxies themselves. That's what these stars are. And here's where the danger comes in. A hypervelocity star is not a tiny bullet. It's a massive sphere of plasma, often several times larger than our sun, moving with that kind of velocity. If speed itself is power, then hypervelocity stars are weapons of unimaginable scale. Their kinetic energy dwarfs anything we could possibly compare it to on Earth. The energy released in a star of that mass, moving at millions of kilometers per hour, is so immense that if such an object passed close to a planetary system, the gravitational disruption alone could tear worlds from their orbits. But let's push the analogy further. On Earth, a supersonic jet, like the Concorde, used to fly at about 2,100 kilometers per hour. That's fast enough to break the sound barrier multiple times over. If we use that as a baseline, hypervelocity stars are traveling at speeds about 1,700 times faster than the Concorde. They are not merely supersonic, they are supragalactic. They operate in a speed regime where human comparisons nearly fail us. The comparison to other astronomical bodies makes their velocity even more astonishing. Comets that fall into the sun from the edges of our solar system might reach 70 kilometers per second at their fastest. Neutron stars, which can also receive kicks from supernova explosions, sometimes shoot across space at a few hundred kilometers per second. But hypervelocity stars surpass even those. They sit at the very top of the cosmic speed chart, rivaled only by the speeds of particles accelerated near black holes. So when astronomers talk about hypervelocity stars traveling at 1,000 to 2,000 kilometers per second, what they're really describing is something that is not just fast, it's transcendently fast. These are stars that laugh in the face of galactic boundaries, outrunning the very thing that binds billions of stars together. In terms of sheer velocity, they are nature's most extreme test cases of what happens when gravity and stellar mass collide in violent, unpredictable ways. And if that velocity still seems abstract, consider this final comparison. At the speed some hypervelocity stars travel, they could cross the entire distance between our sun and its nearest neighbor, Proxima Centauri, in less than 1 million years. That might sound long to us, but in cosmic terms, it's the blink of an eye. A star covering 4.2 light-years in under 1 million years is nothing short of breathtaking. Their speed is not just a number, it is the defining feature that transforms them from ordinary stars into dangerous cosmic bullets, loaded with enough kinetic energy to shape the fates of planetary systems and galaxies alike. We've looked at the sheer velocity of these stellar outlaws, and that speed alone is enough to inspire awe. But speed by itself doesn't tell the whole story of why hypervelocity stars are so extraordinary and so threatening. To really understand the danger they pose, we need to think of them not as distant curiosities, but as what they truly are: cosmic bullets, fired across the galaxy with no regard for what lies in their path. When we talk about danger in an astronomical sense, we're not always talking about direct collisions. Space is vast, unimaginably so, and the odds of a hypervelocity star colliding head-on with another star or planet are vanishingly small. But direct impact isn't necessary for disaster. These stars carry with them enormous gravitational fields. They may be racing through space like bullets, but unlike bullets, they tug at everything around them with invisible hands of gravity. Imagine a hypervelocity star passing anywhere near our solar system. It wouldn't have to smash directly into the sun or Earth to wreak havoc. Its sheer gravitational pull, even from a relatively distant flyby, could distort the delicate orbital balance of our planets. Mercury, Venus, Earth, and Mars could be nudged into slightly different paths. Outer planets like Jupiter and Saturn, with their massive gravitational influence, could be tugged just enough to ripple those effects throughout the solar system. Over thousands or even millions of years, those small changes could destabilize orbits, sending planets, asteroids, or comets spiraling into dangerous new trajectories. Earth itself could be knocked into a colder orbit farther from the sun, or worse, nudged closer, where life would be scorched away. The asteroid belt and the Oort cloud, reservoirs of icy and rocky bodies, are even more vulnerable. A hypervelocity star sweeping near could send countless comets raining inward toward the inner solar system. The bombardment that would follow could resemble the catastrophic impacts that once wiped out the dinosaurs, but on a far greater scale and potentially repeated over long spans of time. Just one such gravitational disturbance could transform our solar system into a shooting gallery of deadly projectiles. And the threat doesn't end with planetary systems like ours. Hypervelocity stars can disrupt star-forming regions too. In dense molecular clouds where new stars are born, a hypervelocity star barreling through could stir up turbulence, compressing some areas while dispersing others. Star formation is a fragile process, dependent on delicate balances of gravity, pressure, and gas density. A sudden gravitational intruder could prevent stars from forming where they might have otherwise emerged, or accelerate collapse in ways that change the distribution of stellar populations. In other words, these runaway stars don't just alter the present, they can reshape the future of galactic evolution itself. The analogy to bullets is apt, but even bullets eventually stop. A hypervelocity star doesn't. Once launched, it keeps going, forever, unless it encounters another strong gravitational source. That endless journey means its potential for danger is not confined to its home galaxy. Over millions or billions of years, it may pass through multiple regions of space, threatening not just one star system, but many. Its trajectory is unpredictable over vast cosmic timescales, but its risk is always real: disruption, destabilization, or destruction on a scale that dwarfs anything humanity could ever engineer. And even the energy they carry makes them dangerous. The kinetic energy of a massive star traveling at over 1,000 kilometers per second is mind-boggling. To give a sense of scale, the energy released by a hypervelocity star in motion is vastly greater than the total energy output of all human civilizations over all of recorded history. If such a star were to directly impact another stellar object, the result would be catastrophic beyond any imagination. Explosions, shock waves, and ejected matter that would ripple through interstellar space for light years. And while it might be tempting to think of them as rare enough to dismiss, rarity is not comfort when we're dealing with objects of the scale. The galaxy is vast, and even a few hypervelocity stars could represent a slow-moving, long-term threat to countless planetary systems. They are reminders that not all dangers in the universe are stationary or predictable. Some threats move silently, relentlessly, at unimaginable speeds. So when astronomers describe hypervelocity stars as dangerous, they're not indulging in exaggeration. They are recognizing that these stars represent one of the few classes of natural objects that, simply by passing near, can reshape or even destroy the stability of entire systems. They don't need to collide. They don't need to explode. Their existence alone, their speed, their mass, their gravitational reach, is enough to make them one of the most menacing travelers in the universe. After understanding the incredible danger hypervelocity stars represent, it's natural to wonder, how did we even find out about them in the first place? These aren't obvious objects, streaking across the night sky like meteors. To the naked eye, even a hypervelocity star looks just like any other distant point of light. They don't announce their speed with trails of fire or dramatic flashes. Instead, their story begins with careful astronomical detective work, the kind that requires patience, precision, and a bit of cosmic luck. The breakthrough came in 2005 when a team of astronomers led by Warren Brown at the Harvard-Smithsonian Center for Astrophysics made an astonishing discovery. They were studying stars near the center of the Milky Way, a region that has always fascinated scientists because it's home to Sagittarius A, the supermassive black hole that anchors our galaxy. The gravitational chaos in that region is extreme, and astronomers suspected that some stars might behave in unusual ways. In the course of their survey, Brown's team found something utterly bizarre, a star that appeared to be traveling so fast that it could possibly not be gravitationally bound to the Milky Way. This star, later designated HVS-1 for Hypervelocity Star 1, was moving at roughly 850 kilometers per second, nearly twice the speed needed to escape the Milky Way's gravitational pull at its location. To astronomers, it was like finding a car speeding at 200 miles per hour down a quiet neighborhood street. It didn't just stand out, it defied expectations. This discovery immediately raised profound questions. How could a star, an object with a mass of the sun or greater, be moving at such astonishing speeds? The physics required to launch something that massive out of a galaxy are staggering. The most likely explanation, even then, pointed towards interactions with the supermassive black hole at the galactic center. It was as if the black hole had acted like a slingshot, hurling the star out of the galaxy after some violent gravitational encounter. The 2005 discovery was not just a curiosity, it opened an entirely new branch of astrophysics. Until then, no one had confirmed the existence of stars moving fast enough to leave their galaxies behind. There had been predictions, of course. In the late 1980s, two theorists, Jack Hills and Martin Rees, had proposed that interactions with a supermassive black hole could fling stars outward at hypervelocities. Their theory suggested that if a binary star system wandered too close to a black hole, one star could be captured, while the other was catapulted outward at incredible speeds. But for years, this idea remained speculative, until Brown's team stumbled upon the very evidence that confirmed it. After HVS-1 was identified, astronomers began to look more carefully for others, and slowly the trickle of discoveries began. More hypervelocity stars were found, each one providing more evidence that the process was real, and not just a theoretical curiosity. By tracing their trajectories, astronomers could often determine that they indeed originated near the galactic center, supporting the hypothesis that Sagittarius A was acting as a kind of cosmic accelerator. The discovery story also underscores how astronomy often advances, not by predicting the obvious, but by stumbling across the improbable. Before 2005, the idea of a star leaving its galaxy was something you might imagine only in extreme simulations. After 2005, it became a reality. The universe had once again shown that it was stranger, more violent, and more dynamic than we had dared to assume. What made the discovery even more remarkable was its timing. Just as technology was improving, telescopes becoming more precise, and instruments like the Sloan Digital Sky Survey providing detailed maps of the stars, the tools to detect such rare objects were falling into place. Without these advances, HVS-1 might have slipped by unnoticed, its story lost among the billions of other stars in the sky. The confirmation of hypervelocity stars also reshaped the way astronomers looked at our own galaxy. If stars could be ejected at such speeds, then the Milky Way was not a closed, stable system of stars orbiting neatly forever. Instead, it was a dynamic, restless place where even entire suns could be hurled into intergalactic exile. The discovery was not just about one star, it was about rewriting our understanding of galactic dynamics, black hole interactions, and the sheer violence lurking at the heart of galaxies. And since that first discovery in 2005, dozens more hypervelocity stars have been identified.
Each one tells its own story, but all trace their lineage back to that pivotal moment when HVS-1 forced astronomers to confront a new reality. Galaxies are not just cradles of stars, they are also cannons, and sometimes they fire.
The binary breakup mechanism also broadens our understanding of how diverse the pathways to hypervelocity status can be. It reminds us that these runaway suns are not defined by a single origin, but by a family of violent processes that all share one thing in common: disruption. Whether it's the merciless tug of a black hole or the furious death throes of a supernova, the end result is the same. A star, once bound, is now free, launched into the cosmic wilderness at impossible speeds. Binary breakups offer a glimpse of how violence within a single stellar system can create hypervelocity stars. Yet, as dramatic as those processes are, they occur on a relatively local scale, within a single star system or the central regions of a galaxy. There is, however, an even larger stage upon which the universe orchestrates extreme events: the collision of galaxies themselves. These cataclysmic encounters are slow-motion cosmic train wrecks, lasting millions or even billions of years, and they are capable of creating hypervelocity stars on a scale that dwarfs anything happening in individual star systems. Galaxies are not isolated. They drift through space, orbit clusters of other galaxies, and over cosmic timescales, gravitational attraction inevitably leads to encounters. Sometimes two galaxies merge in a slow, drawn-out dance of gravity. During such events, stars, gas clouds, dark matter, and even supermassive black holes interact in highly complex ways. While stars themselves are separated by vast distances, meaning direct collisions are rare, the gravitational forces at play can accelerate stars to extreme velocities. When two galaxies begin to merge, tidal forces stretch and distort their shapes. Streams of stars, known as tidal tails, are pulled away from the galactic cores, forming long, arching filaments of light. Within these chaotic regions, certain stars can experience extreme gravitational slingshots. The combined gravitational pull of dense galactic cores, dark matter concentrations, and massive star clusters can catapult stars to velocities high enough to exceed the escape speed of the newly forming galaxy or even the original galaxies. These stars, born in the violent chaos of galactic mergers, are essentially flung into intergalactic space as hypervelocity refugees. One of the most striking aspects of galaxy-induced hypervelocity stars is the sheer scale of energy involved. Individual stars being ejected from a binary system or by a black hole are violent, yes, but they involve relatively small numbers of stars at a time. In contrast, galaxy collisions involve billions of stars, and the gravitational interplay of these enormous masses can send multiple stars flying at thousands of kilometers per second simultaneously. Over the course of the merger, many stars may be permanently expelled, creating a population of hypervelocity stars that eventually drift through intergalactic space far from any galactic home. Observational evidence supports this mechanism. Astronomers studying merging galaxies like the antennae galaxies, NGC 4038 and 4039, have detected stars in tidal streams moving at speeds far higher than typical orbital velocities. While most of these stars remain gravitationally bound to the merged galaxy, a subset exhibits trajectories suggesting they are unbound, destined to wander between galaxies indefinitely. Simulations of galaxy mergers also predict that such ejections are common, particularly in interactions involving galaxies of unequal size or when supermassive black holes at their centers interact gravitationally. This process also highlights the role of dark matter in shaping hypervelocity stars. While invisible to telescopes, dark matter exerts gravitational forces just like ordinary matter. During a galaxy collision, concentrations of dark matter can amplify tidal forces and gravitational interactions, increasing the likelihood that stars will be accelerated to hypervelocity. In this sense, hypervelocity stars produced during mergers are not just relics of visible galactic chaos, they are also indirect messengers of dark matter distribution. Observing their trajectories allows astronomers to infer the otherwise hidden gravitational architecture of galaxies. Unlike hypervelocity stars produced near a black hole or from binary breakups, those generated in galaxy mergers can come from any part of the galaxy, not just its center. Stars in the outskirts of galactic disks or in loosely bound clusters are particularly vulnerable to ejection. Once flung into intergalactic space, these stars carry the imprint of their tumultuous past. High velocities, unusual trajectories, and sometimes even chemical compositions that hint at the unique regions of their birth. The creation of hypervelocity stars during galaxy collisions also underscores the dynamic nature of the universe on the largest scales. While humans tend to think of galaxies as static islands of stars, in reality they are constantly interacting, growing, merging, and reshaping the cosmos. Each collision, while slow on human timescales, is capable of producing runaway stars traveling millions of kilometers per hour, contributing to the population of stellar exiles that roam the void between galaxies. These are not random occurrences. They are a natural consequence of gravitational physics on the grandest scales. It's worth noting that some hypervelocity stars observed in the Milky Way may have originated from dwarf galaxies that merged with or were absorbed by the Milky Way in the distant past. Their high velocities and trajectories may not be tied to the central black hole, but instead to gravitational interactions during these galactic mergers. In this way, hypervelocity stars can serve as fossil records, providing clues to the Milky Way's own violent history of growth and assimilation. So while galaxy center ejections and binary breakups give us examples of how extreme forces on smaller scales can produce hypervelocity stars, galaxy collisions show that these processes also operate on cosmic scales. Entire stellar populations can be accelerated and scattered, and some of these stars will ultimately travel beyond the boundaries of any galaxy, joining the ranks of solitary wanderers. In the universe, speed and violence are not limited to individual stars. They can emerge from the collective gravitational ballet of billions of stars moving through space together. Having explored how hypervelocity stars are forged, whether slingshotted by black holes, blasted from binary systems, or hurled during galaxy collisions, it becomes essential to grasp the scale of the feat they accomplish. To leave a galaxy behind is not simply a matter of moving fast, it's about overcoming one of the most fundamental forces in the universe, gravity. This is where the concept of escape velocity comes into play, and why hypervelocity stars are truly extraordinary. Every galaxy exerts a gravitational pull on the stars within it. This gravity is not uniform, it's strongest near the galaxy center where stars, gas, and dark matter are densest, and weaker at the outskirts of the galactic disk. For a star to leave the galaxy forever, it must achieve a speed that overcomes the cumulative gravitational attraction of the entire galactic mass. This critical speed is what astronomers call the escape velocity. For the Milky Way, this value is roughly 550 kilometers per second, or about 2 million kilometers per hour. To put this into perspective, the Sun, orbiting the center of the Milky Way at around 220 kilometers per second, is moving fast in human terms, yet it is still securely bound to the galaxy. Even if the Sun were moving twice as fast, it would still orbit the galactic center like a planet orbiting a star, never escaping, never wandering beyond the Milky Way. This highlights just how exceptional hypervelocity stars are. They not only meet the escape velocity, they exceed it, often by significant margins. Achieving escape velocity is not trivial. It requires a combination of precise gravitational interactions and frequently extraordinary luck in timing and trajectory. A star must gain velocity in just the right direction to break free.
For example, a binary star disrupted by a black hole will only produce a hypervelocity star if the surviving star is flung outward along a trajectory that opposes the gravitational pull of the galactic center. Similarly, stars ejected during galaxy mergers must gain enough speed in the right vector to overcome the combined gravitational pull of both colliding galaxies. Even a slight misalignment can leave the star bound, orbiting in the galactic halo, or eventually returning toward the galactic center.
It's also important to note that escape velocity is not a fixed number. It depends on the star's location within the galaxy. Near the dense central bulge, escape velocities are higher, potentially exceeding 1,000 kilometers per second, while in the outer halo they can be lower, closer to 400 kilometers per second. A hypervelocity star capable of leaving the Milky Way must therefore achieve velocities that not only meet, but surpass these thresholds, depending on where it begins its journey. This requirement makes her detection and study even more fascinating. Each hypervelocity star is a record of an extreme, carefully calibrated cosmic event. Beyond the Milky Way, escape velocities vary widely among galaxies. Dwarf galaxies with smaller masses may have escape velocities as low as tens of kilometers per second, meaning a star could be more easily ejected. In massive elliptical galaxies, escape velocities can approach 1,500 kilometers per second, making hypervelocity stars in such environments even rarer and more extraordinary. The concept of escape velocity thus provides a universal framework for understanding just how extreme hypervelocity stars are, no matter where they originate. One of the reasons hypervelocity stars capture astronomers' imaginations is precisely this challenge. Traveling at or above 550 kilometers per second is not just a statistic. It represents the ability to leave a galaxy that contains billions of stars, countless planets, and an enormous mass of dark matter. Hypervelocity stars are not merely fast. They are exceptional survivors of processes powerful enough to give them a cosmic passport, freeing them from the galaxy's gravitational prison. Furthermore, the need to exceed escape velocity explains why hypervelocity stars are so rare. Most stars, even those affected by dynamic processes like supernovae or black hole interactions, gain only modest increases in velocity. The conditions required to push them past the escape threshold are extreme, and only the most violent interactions, like those near supermassive black holes or during galactic mergers, can provide them. This is why the discovery of even a single hypervelocity star is a monumental event for astronomers. It represents a star that has undergone a nearly unimaginable journey, both violent and precise, to achieve galactic freedom. In essence, hypervelocity stars are extraordinary because they defy the gravitational norms that govern the cosmos. While billions of stars will orbit their galaxies for eons, a hypervelocity star is fundamentally different. It has enough energy to leave its home behind and drift through intergalactic space. Its journey is no longer dictated by the gravitational pull of the Milky Way, but by the inertia and momentum gifted to it during its violent ejection. These stars are living proof that the universe is not just a place of orderly orbits and gentle rhythms, it is a place of extreme forces and unpredictable outcomes, where even massive celestial bodies can be sent hurtling into the void. Now that we've explored escape velocities and the immense forces required to leave a galaxy, it's important to clarify a distinction that often confuses even seasoned astronomy enthusiasts: the difference between runaway stars and hypervelocity stars. While both categories involve stars moving faster than typical, the consequences and mechanisms behind their motion are remarkably different. Understanding this difference will deepen our appreciation for just how extraordinary hypervelocity stars are. Runaway stars are relatively common compared to hypervelocity stars. They are stars that have acquired unusually high speeds relative to their surrounding stellar population, but remain gravitationally bound to their host galaxy. Typically, these stars move at hundreds of kilometers per second, fast enough to stand out in velocity surveys, but not nearly fast enough to escape the galaxy. Most runaway stars originate from binary star disruptions or dynamical interactions in dense star clusters. For example, consider a binary system in which one star explodes as a supernova. The surviving star, previously orbiting its companion, suddenly finds itself unbound, and its velocity can spike to several hundred kilometers per second. It will race through the galaxy, but unless that velocity exceeds the escape threshold, roughly 550 kilometers per second for the Milky Way, it will eventually settle into a new orbit within the galaxy.
Similarly, in dense star clusters where many stars interact gravitationally, a close encounter can fling a star outward at high speed. These stars, however, typically remain gravitationally tethered to the galaxy, and their high velocities manifest as peculiar motions relative to neighboring stars. Hypervelocity stars, on the other hand, are in a completely different league. They are stars moving so fast that they exceed the escape velocity of the Milky Way, and they're on trajectories that carry them out of the galaxy entirely. Unlike runaway stars, which remain orbiting in the galactic halo, hypervelocity stars are true exiles, destined to wander intergalactic space indefinitely. Achieving hypervelocity requires an extraordinarily energetic event, such as an interaction with a supermassive black hole or the combined gravitational forces during galactic mergers, which can impart thousands of kilometers per second to a single star. The key distinction is not just speed, but freedom from gravitational bondage. Another way to conceptualize the difference is to imagine a racetrack. A runaway star is like a sprinter who has broken from the pack and is running unusually fast around the track, but is still bound by the circular path of the course. A hypervelocity star, by contrast, is like a sprinter who breaks through the barriers entirely, flying off the track and into open terrain that was previously inaccessible. This freedom makes hypervelocity stars both rare and far more scientifically intriguing. They are messengers of extreme events and interactions, carrying information about black holes, galaxy dynamics, and even the dark matter distribution of the Milky Way. Observationally, the distinction can also be seen in trajectory analysis. Runaway stars tend to have high velocities relative to the local stellar neighborhood, but follow paths that curve around the galaxy center. Hypervelocity stars, in contrast, often have radial trajectories pointing away from the galaxy core, indicating that they were ejected with sufficient speed to escape the galaxy entirely. This is why careful measurements of both speed and direction are critical for astronomers when classifying a star as hypervelocity. Misclassifying a runaway star as hypervelocity can happen if only its speed is considered without analyzing its path and gravitational context. The difference between the two types of stars also underscores the rarity and significance of hypervelocity stars. While runaway stars are relatively numerous and can tell us about local stellar interactions or supernova physics, hypervelocity stars are exceptional events, often born from the universe's most extreme and violent interactions. Each one is effectively a cosmic experiment in acceleration, a probe that carries with it clues about the forces that expelled it, the environment it originated from, and the galactic structure it once called home. In short, runaway stars are fast, interesting, and informative, but they are still part of their galaxy's gravitational family. Hypervelocity stars, on contrast, have broken free entirely. They are stellar exiles, wandering the intergalactic void at speeds that make ordinary galactic dynamics almost irrelevant. Recognizing this distinction is crucial for understanding the scale of violence, energy, and galactic mechanics involved in their creation. It's this freedom from galactic constraints that elevates hypervelocity stars from merely unusual to truly extraordinary, making them one of the universe's most fascinating phenomena. Having clarified the distinction between runaway stars and hypervelocity stars, it's natural to turn to actual observations. While much of what we've discussed so far is theoretical or derived from models, astronomers have indeed identified real hypervelocity stars, each carrying its own story of violent ejection, incredible speed, and cosmic exile. Observing these stars is no small feat. They are rare, often distant, and can easily be lost among billions of ordinary stars. Yet each confirmed detection reinforces our understanding of how dynamic and violent the universe can be. The first confirmed hypervelocity star, HVS-1, was discovered in 2005 by the team led by Warren Brown at the Harvard-Smithsonian Center for Astrophysics. HVS-1 provided the first observational proof that stars could actually be ejected from the Milky Way entirely, confirming decades of theoretical predictions. This star is moving at roughly 850 kilometers per second, fast enough to overcome the Milky Way's gravitational pull. Its velocity, trajectory, and composition indicate that it likely originated near the galaxy center, where the supermassive black hole, Sagittarius A, served as the cosmic accelerator in its violent journey. The discovery of HVS-1 was groundbreaking because it provided astronomers with tangible evidence that Hill's theoretical mechanism, binary star disruption by a supermassive black hole, was indeed producing real hypervelocity stars.
Another particularly dramatic example is S5 HVS1, discovered much more recently.
S5 HVS1 is extraordinary because of its incredible speed, measured at roughly 1,700 kilometers per second, making it one of the fastest stars ever observed. To put that in perspective, S5 HVS1 is moving at nearly 6 million kilometers per hour, or over 7 times faster than the Sun's orbit around the galactic center. Its trajectory points almost directly away from the galactic center, providing a near-ideal example of a star likely ejected by a close interaction with Sagittarius A. The precision of its motion allowed astronomers not only to confirm its hypervelocity status, but also to trace its origin with remarkable confidence. This star was, quite literally, shot out of the Milky Way's core like a cannonball. There are other hypervelocity stars as well, though they are rarer and often more difficult to study due to distance and faintness. Stars like HVS2, HVS3, and HVS7 have all been identified, with velocities ranging from 600 to 1,000 kilometers per second. Some of these stars are located in the galactic halo, tens of thousands of light years away from the plane of the Milky Way, highlighting how far and wide these stellar exiles can travel. HVS3, for example, was found to be unusually massive and young for its location in the halo, suggesting it had been ejected at high velocity rather than formed in place, a direct indicator of the violent process that expelled it. Each observed hypervelocity star provides crucial scientific insight. By measuring their velocities and directions, astronomers can reconstruct the gravitational interactions that launched them. In some cases, these stars help map the gravitational potential of the Milky Way, offering indirect clues about the distribution of dark matter. Others provide evidence for the dynamics near the supermassive black hole, where extreme gravitational forces dominate. Observing hypervelocity stars is therefore not just about cataloging rare cosmic phenomena. It's about using them as tools to probe the hidden structure and history of our galaxy. In essence, these observed hypervelocity stars transform the concept from theory into reality. HVS1 showed us that such objects exist. S5 HVS1 shocked us with the sheer extremity of speed achievable. Others like HVS3 and HVS7 illustrate the variety of properties these stars can have, including mass, composition, and trajectory. Together, they paint a picture of a galaxy that is not static, but highly dynamic, where extreme forces can take ordinary stars and turn them into extraordinary intergalactic travelers. Each observation reinforces the understanding that hypervelocity stars are not just theoretical curiosities, they are living, moving proof of the violent and unpredictable nature of the cosmos. Once a star achieves hypervelocity and breaks free from its galactic home, its existence enters a entirely new phase, one of isolation, wandering, and permanence in the vast emptiness of intergalactic space. Unlike stars bound to galaxies, which continue orbiting the galactic center for billions of years, hypervelocity stars are cast out as cosmic exiles, leaving behind not only their birthplace, but also the familiar gravitational framework that once structured their lives. Their fate is as lonely as it is extraordinary. After ejection, a hypervelocity star travels along a nearly linear trajectory, with little chance of returning to its galaxy. Bound only by inertia, the star moves through the intergalactic medium, a space that is astonishingly empty, about 1 atom per cubic centimeter on average. For perspective, a hypervelocity star crossing this expanse experiences a near total absence of matter to interact with, which means it can travel for billions of years without slowing down in any meaningful way. Unlike stars in dense galactic environments, there are no nearby gravitational interactions to alter their course significantly. Their motion is dictated largely by the initial force of their ejection. Timescales in intergalactic space are staggering. A hypervelocity star ejected from the Milky Way today might travel hundreds of thousands of light years in a single million-year period. Even the closest galaxy, Andromeda, lies about 2.5 million light years away. Hypervelocity stars could, over the course of their lifetimes, traverse these immense distances, perhaps passing through the gravitational outskirts of other galaxies without ever being captured. For the majority of their existence, they will be solitary travelers moving through the cold, dark void of space as the universe expands around them. Their physical and observable characteristics remain largely unchanged during their solitary journey.
Nuclear fusion continues at their cores and they shine as regular stars would, though their luminosity might fade with distance if they are massive and exhausting fuel quickly. Smaller, longer-lived stars, like red dwarfs, could persist as hypervelocity stars for trillions of years, effectively drifting eternally through space, light traveling unimpeded for incomprehensible distances. Massive stars, in contrast, burn through their fuel rapidly and end their lives as supernovas or neutron stars, still traveling at hypervelocity. In some cases, the remnants themselves, white dwarfs, neutron stars, or black holes, could continue their lonely journeys across intergalactic space, extending the legacy of the ejection event even further. One of the most remarkable aspects of their fate is the profound isolation these stars experience. Within galaxies, stars are part of complex gravitational and ecological systems. They form clusters, influence star formation in surrounding clouds, and interact dynamically with neighbors. Hypervelocity stars, however, are severed from these networks. They will not encounter new planetary systems regularly, nor will they participate in the ongoing evolution of a galaxy's stellar population. Each hypervelocity star becomes, in a sense, a solitary witness to the universe, a traveling monument to the violent forces that expelled it, carrying the memory of its home galaxy through empty space. Despite this isolation, these stars are far from irrelevant. Even as they wander alone, they serve as cosmic messengers. Their trajectories, velocities, and chemical compositions preserve clues about the gravitational forces that created them, the regions of the galaxy they originated from, and even the presence of dark matter. Astronomers can study hypervelocity stars to infer properties of their parent galaxies long after the stars have left. In other words, while these stars themselves may drift in solitude, their scientific value extends far beyond their lonely paths. Interestingly, hypervelocity stars could even act as a bridge between galaxies. Over billions of years, some might pass near other galaxies, potentially entering their outskirts or halos. While capture is rare, the possibility exists, meaning that a star ejected from the Milky Way today could one day become part of another galaxy's periphery, effectively serving as an intergalactic traveler that has journeyed vast distances. But for the vast majority, their destiny is permanent exile. Billions of years of solitary motion through the cold, expanding universe, carrying with them the story of the violence that launched them and the imprint of the galaxy they left behind. In essence, the fate of hypervelocity stars is a story of cosmic loneliness, endurance, and persistence. They are stars that have broken free from the gravitational chains of their home, surviving as luminous sentinels in a nearly empty universe, drifting forever through intergalactic space. They exemplify both the raw power of cosmic forces and the isolation inherent in extreme trajectories. Their existence is a testament to the extraordinary dynamism of the universe. Even seemingly eternal objects like stars are not bound indefinitely, and the cosmos continually reshapes itself through processes that can send entire suns on journeys across unimaginable distances. Now that we understand the fate of hypervelocity stars as solitary wanderers in intergalactic space, it's both terrifying and fascinating to consider a hypothetical scenario. What if one of these stellar missiles were to enter our solar system? The odds of such an event are astronomically low, but the consequences, if it happened, would be extraordinary, enough to reshape planetary orbits, trigger celestial chaos, and alter the very structure of our solar system. Imagine a star moving at 1,000 kilometers per second, fast enough to escape the Milky Way, approaching the outskirts of our solar system. Even at distances far beyond Pluto, the gravitational influence of a hypervelocity star would not be negligible. While the star itself is not colliding with planets directly, its enormous mass, often comparable to or exceeding that of our Sun, creates a gravitational field capable of tugging at every object in the solar system: planets, dwarf planets, asteroids, comets, and the countless icy bodies residing in the Oort cloud.
The first region to feel the influence of the star would likely be the outer solar system. The Oort cloud, a vast spherical shell of icy bodies extending up to 100,000 astronomical units or AU from the Sun, would be extremely vulnerable. The sudden gravitational tug could dislodge comets from their stable orbits, sending them plunging into the inner solar system. This would create a dramatic increase in cometary bombardments, potentially hundreds or thousands of icy bodies raining toward the inner planets. Earth, Mars, and Venus could face impacts on a scale unprecedented in their histories. Even if planets themselves remain largely unaffected initially, these small bodies could act as cosmic wrecking balls over time. Closer to the Sun, the planets would not escape unscathed. Even a distant passage could perturb planetary orbits, changing eccentricities and inclinations. Mercury and Mars, being smaller and less massive, could experience significant orbital shifts, possibly destabilizing resonances with neighboring planets. Jupiter and Saturn, with their immense masses, might act as stabilizers or amplifiers of the disruption, creating cascading gravitational effects that ripple across the entire system. Over centuries or millennia, these small changes could compound, leading to orbital chaos and potential collisions between planets or with asteroids. The asteroid belt nestled between Mars and Jupiter would also be highly susceptible. Hypervelocity stars could shift the belt structure, sending clusters of asteroids into intersecting orbits with the inner planets. While collisions on a galactic scale are unlikely, the cumulative effect over thousands of years could dramatically increase the risk of catastrophic impacts. In other words, even a near miss by a hypervelocity star could effectively turn the solar system into a chaotic, dynamically unstable environment. Moreover, the sheer kinetic energy of such a star amplifies the potential danger. A hypervelocity star moving at over 1,000 kilometers per second carries energy orders of magnitude greater than any stellar or planetary event we experience locally. Even without direct collisions, the gravitational interactions alone are enough to act as a massive reshuffling force, bending trajectories and destabilizing delicate orbital balances. The effect would be magnified if the star were particularly massive, several times the mass of our Sun, because gravitational influence scales directly with mass.
Finally, there is a psychological and scientific fascination with this scenario. It underscores just how dynamic and interconnected the cosmos is. Even the Sun, planets, and Earth, our apparently stable cosmic neighborhood, are not immune to the violent forces that govern stars on galactic scales. Hypervelocity stars are not just distant curiosities. They are reminders that the universe is full of objects moving at extreme speeds, capable of reshaping systems entirely if their paths intersect with ours. In essence, a hypervelocity star passing through the solar system would act as a cosmic disruptor of unprecedented scale. It wouldn't need to collide with anything directly. Its gravitational reach alone could destabilize orbits, trigger comet showers, and potentially alter the evolutionary trajectory of the planets. While purely hypothetical, this scenario reinforces the awe-inspiring power of hypervelocity stars and the delicate balance of forces that allow our solar system to remain stable across billions of years. If the idea of a hypervelocity star intruding upon our solar system evokes a sense of cosmic peril, understanding the energy they carry only deepens that impression. These stars are not just fast, they are powerhouses of kinetic energy, moving with velocities that transform them into unstoppable forces when they encounter matter, gravity, or dense regions of space. To fully appreciate their impact, it's necessary to explore both the scale of that energy and its consequences. Kinetic energy, in its simplest form, is determined by the mass of an object multiplied by the square of its velocity, divided by 2. Hypervelocity stars, often comparable in mass to the Sun, roughly 2 times 10 to the 30 kilograms, traveling at speeds of 1,000 kilometers per second or more, carry energy so enormous they almost defy human comprehension. For perspective, consider that the total energy output of all human civilization across its entire history pales in comparison to a single hypervelocity star in motion for just a moment. Even a star with half the mass of the Sun moving at 1,500 kilometers per second like S5 HVS1, contains kinetic energy exceeding 10 to the 46 joules. That's more than 1 trillion times the energy released by the most powerful nuclear weapons ever detonated on Earth. This is not theoretical hyperbole. In dense regions of space, star clusters, molecular clouds, or galactic cores, if a hypervelocity star was to pass through, it would act as a gravitational wrecking ball. Its velocity means it interacts only briefly with other objects, but the mass and momentum it carries would exert a sudden, enormous gravitational pull, reshaping the trajectories of surrounding stars, planets, and gas clouds. Molecular clouds, which are the birthplaces of new stars, are particularly susceptible. A hypervelocity star passing nearby could compress certain regions, triggering premature collapse and star formation in one area while dispersing gas in another, halting potential star formation entirely. The resulting changes ripple outward, affecting stellar nurseries for thousands of light years. In the case of star clusters, which are already tightly packed with hundreds or thousands of stars, the energy of a hypervelocity star is sufficient to eject multiple stars from the cluster. Its passage can destabilize gravitational equilibria, causing stars to scatter at velocities far exceeding what they had before. Essentially, it acts like a pinball striking a tightly grouped cluster, sending stellar bodies hurtling into new orbits or even out of the cluster entirely. This is why astronomers often study hypervelocity stars not just for their individual properties, but for what their motion reveals about the environments they pass through. Even in the comparatively empty space of the galactic halo, hypervelocity stars maintain their energy over enormous distances. Unlike smaller objects like comets or asteroids that can be slowed by interstellar gas or minor gravitational tugs, the inertia of a hypervelocity star ensures it continues its path virtually unimpeded for billions of years. Its kinetic energy cannot easily be dissipated. It is a star on a one-way journey, unstoppable unless it encounters a gravitational behemoth capable of significantly altering its trajectory, like another supermassive black hole or a dense galactic core. Another way to contextualize this energy is to consider the consequences of a direct collision. While the probability of a hypervelocity star colliding with another star or dense object is infinitesimally small, the impact would be catastrophic. The kinetic energy of a single hypervelocity star is sufficient to obliterate a planetary system or trigger a stellar disruption. A collision with a molecular cloud could compress enough gas to initiate massive star formation almost instantly, while a close passage could generate tidal forces strong enough to tear apart smaller stars or protoplanetary systems. In essence, these stars are moving energy bombs, carrying with them the raw potential to alter whatever they encounter, even if only briefly. It's also important to note that hypervelocity stars maintain their energy as the universe expands. Over millions or billions of years, their velocity decreases only slightly due to gravitational interactions, meaning that their energy remains largely intact throughout their intergalactic journeys. This makes them unique cosmic projectiles, capable of exerting influence over enormous distances. Even when drifting alone in the intergalactic medium, they are carriers of kinetic power far beyond anything encountered in more typical astrophysical scenarios. The energy hypervelocity stars carry is not only a measure of their speed and mass, but a symbol of the raw dynamism of the cosmos. These are stars that can travel unbound, resisting gravitational constraints, reshaping regions of space, and carrying momentum that can last for billions of years. Unlike slower-moving stars, they are not passive participants in the galaxy's evolution. They are agents of change, unstoppable and enduring, whose motion encapsulates both the violence and the beauty of the universe at its most extreme. Even with all their power and velocity, hypervelocity stars are remarkably elusive. Detecting these celestial speedsters is one of the greatest challenges in modern astronomy, and their rarity only compounds the difficulty. The very factors that make them extraordinary, their incredible speed, their vast journeys through space, and their isolation from galaxies, also make them incredibly hard to find. Understanding the challenges of detection illuminates just how much effort and ingenuity it takes to study these intergalactic wanderers. Finally, there is a psychological and scientific fascination with this scenario. It underscores just how dynamic and interconnected the cosmos is. Even the Sun, planets, and Earth, our apparently stable cosmic neighborhood, are not immune to the violent forces that govern stars on galactic scales. Hypervelocity stars are not just distant curiosities. They are reminders that the universe is full of objects moving at extreme speeds, capable of reshaping systems entirely if their paths intersect with ours. In essence, a hypervelocity star passing through the solar system would act as a cosmic disruptor of unprecedented scale. It wouldn't need to collide with anything directly. Its gravitational reach alone could destabilize orbits, trigger comet showers, and potentially alter the evolutionary trajectory of the planets. While purely hypothetical, this scenario reinforces the awe-inspiring power of hypervelocity stars and the delicate balance of forces that allow our solar system to remain stable across billions of years. If the idea of a hypervelocity star intruding upon our solar system evokes a sense of cosmic peril, understanding the energy they carry only deepens that impression. These stars are not just fast, they are powerhouses of kinetic energy, moving with velocities that transform them into unstoppable forces when they encounter matter, gravity, or dense regions of space. To fully appreciate their impact, it's necessary to explore both the scale of that energy and its consequences. Kinetic energy, in its simplest form, is determined by the mass of an object multiplied by the square of its velocity, divided by 2. Hypervelocity stars, often comparable in mass to the Sun, roughly 2 times 10 to the 30 kilograms, traveling at speeds of 1,000 kilometers per second or more, carry energy so enormous they almost defy human comprehension. For perspective, consider that the total energy output of all human civilization across its entire history pales in comparison to a single hypervelocity star in motion for just a moment. Even a star with half the mass of the Sun, moving at 1,500 kilometers per second like S5 HVS1, contains kinetic energy exceeding 10 to the 46 joules. That's more than 1 trillion times the energy released by the most powerful nuclear weapons ever detonated on Earth. This is not theoretical hyperbole. In dense regions of space, star clusters, molecular clouds, or galactic cores, if a hypervelocity star was to pass through, it would act as a gravitational wrecking ball. Its velocity means it interacts only briefly with other objects, but the mass and momentum it carries would exert a sudden, enormous gravitational pull, reshaping the trajectories of surrounding stars, planets, and gas clouds. Molecular clouds, which are the birthplaces of new stars, are particularly susceptible. A hypervelocity star passing nearby could compress certain regions, triggering premature collapse and star formation in one area while dispersing gas in another, halting potential star formation entirely. The resulting changes ripple outward, affecting stellar nurseries for thousands of light years. In the case of star clusters, which are already tightly packed with hundreds or thousands of stars, the energy of a hypervelocity star is sufficient to eject multiple stars from the cluster. Its passage can destabilize gravitational equilibria, causing stars to scatter at velocities far exceeding what they had before. Essentially, it acts like a pinball striking a tightly grouped cluster, sending stellar bodies hurtling into new orbits or even out of the cluster entirely. This is why astronomers often study hypervelocity stars not just for their individual properties, but for what their motion reveals about the environments they pass through. Even in the comparatively empty space of the galactic halo, hypervelocity stars maintain their energy over enormous distances. Unlike smaller objects like comets or asteroids that can be slowed by interstellar gas or minor gravitational tugs, the inertia of a hypervelocity star ensures it continues its path virtually unimpeded for billions of years. Its kinetic energy cannot easily be dissipated. It is a star on a one-way journey, unstoppable unless it encounters a gravitational behemoth capable of significantly altering its trajectory, like another supermassive black hole or a dense galactic core. Another way to contextualize this energy is to consider the consequences of a direct collision. While the probability of a hypervelocity star colliding with another star or dense object is infinitesimally small, the impact would be catastrophic.
The kinetic energy of a single hypervelocity star is sufficient to obliterate a planetary system or trigger a stellar disruption. A collision with a molecular cloud could compress enough gas to initiate massive star formation almost instantly, while a close passage could generate tidal forces strong enough to tear apart smaller stars or protoplanetary systems. In essence, these stars are moving energy bombs, carrying with them the raw potential to alter whatever they encounter, even if only briefly. It's also important to note that hypervelocity stars maintain their energy as the universe expands. Over millions or billions of years, their velocity decreases only slightly due to gravitational interactions, meaning that their energy remains largely intact throughout their intergalactic journeys. This makes them unique cosmic projectiles, capable of exerting influence over enormous distances. Even when drifting alone in the intergalactic medium, they are carriers of kinetic power far beyond anything encountered in more typical astrophysical scenarios. The energy hypervelocity stars carry is not only a measure of their speed and mass, but a symbol of the raw dynamism of the cosmos. These are stars that can travel unbound, resisting gravitational constraints, reshaping regions of space, and carrying momentum that can last for billions of years. Unlike slower-moving stars, they are not passive participants in the galaxy's evolution. They are agents of change, unstoppable and enduring, whose motion encapsulates both the violence and the beauty of the universe at its most extreme. Even with all their power and velocity, hypervelocity stars are remarkably elusive. Detecting these celestial speedsters is one of the greatest challenges in modern astronomy, and their rarity only compounds the difficulty. The very factors that make them extraordinary, their incredible speed, their vast journeys through space, and their isolation from galaxies, also make them incredibly hard to find. Understanding the challenges of detection illuminates just how much effort and ingenuity it takes to study these intergalactic wanderers.
First, consider distance. Hypervelocity stars are not only rare, they often travel to the far reaches of the galactic halo, or even beyond the Milky Way entirely. Many of them are tens of thousands of light years away from the Sun, meaning their light is extremely faint by the time it reaches Earth. Even powerful telescopes can struggle to differentiate them from the dense backdrop of ordinary stars. Their apparent brightness diminishes with the square of the distance, so a star that is inherently luminous can still be nearly invisible if it is too far away. For smaller or less massive hypervelocity stars, detection is even harder. Their faint light can easily be lost among millions of other faint stars in the galaxy or masked by interstellar dust. Second, their motion is deceptive. Hypervelocity stars do not blaze across the sky like meteors. They drift as ordinary points of light, moving incredibly fast relative to the galaxy, but appearing almost stationary from Earth over short timescales. Astronomers can't simply look at the sky and see them streaking past. Detecting them requires precise measurements of their radial velocity, the component of motion along the line of sight, and proper motion across the sky. These measurements involve spectroscopic analysis to detect the Doppler shift of light, which can indicate whether a star is moving toward or away from us at unusually high speeds. Even slight errors in measurement can make the difference between identifying a true hypervelocity star and mistaking it for a fast-moving but bound star. Complicating matters further, many hypervelocity stars are young, massive, and short-lived. While massive stars shine brightly, they exhaust their fuel quickly and may go supernova before traveling very far, limiting the window in which we can detect them. Older, lower-mass stars last longer but are far dimmer, making their detection more reliant on extremely sensitive instruments. The combination of rarity, distance, and faintness means that only a tiny fraction of hypervelocity stars have been observed so far, and many more likely exist undetected. Interstellar and intergalactic medium also pose obstacles. Gas and dust within the Milky Way can absorb and scatter light, particularly in the galactic plane where many hypervelocity stars may originate. As these stars leave the dense regions of the galaxy and enter the halo or intergalactic space, their surroundings become emptier, but their apparent luminosity decreases and they fade into the darkness of the cosmic void. Observing such stars requires not only highly sensitive telescopes, but also careful selection of observational fields to avoid regions where extinction is severe or where background stars create confusion. Moreover, distinguishing hypervelocity stars from other high-speed stars is a delicate process. Runaway stars, halo stars with peculiar velocities, and stars in binary systems can mimic the apparent motion of a hypervelocity star. Astronomers must meticulously trace a star's trajectory and combine measurements of velocity, position, and stellar properties to confirm that it is truly on an unbound path out of the galaxy. Even with advanced surveys, this confirmation can take years, requiring repeated observations to reduce uncertainties and account for potential errors. Despite these challenges, advances in technology have greatly improved our ability to find hypervelocity stars. Space-based observatories like Gaia provide precise astrometric data for billions of stars, allowing astronomers to measure proper motions and detect candidates moving unusually fast. Large spectroscopic surveys, such as the Sloan Digital Sky Survey, complement this by measuring radial velocities, chemical compositions, and distances. Upcoming facilities like the Vera Rubin Observatory are expected to expand these discoveries even further, capable of detecting faint, fast-moving stars across much larger portions of the sky. Yet, even with these tools, hypervelocity stars remain a tiny needle in a cosmic haystack. Their rarity, isolation, and faintness make every confirmed detection a triumph of both technology and patience. Each discovery provides not only a new object of study, but also critical insight into galactic dynamics, black hole physics, and the structure of the Milky Way's halo. Detecting hypervelocity stars is like spotting a lone runner in an endless desert, impossible to track without careful observation, but when identified, the information it carries is invaluable. In essence, the challenge of detection underscores how elusive hypervelocity stars truly are. They are not only extraordinary in motion and energy, but also in their scarcity and hidden nature. Every observation is a reminder that these stars, despite their immense power, are delicate messengers, fading into the darkness as they traverse the vast expanses of intergalactic space. Their elusiveness is part of their mystique, and it is precisely this challenge that makes each confirmed hypervelocity star a remarkable window into the violent and dynamic processes that shape our universe. Hypervelocity stars are not just fascinating anomalies. They also serve as critical tools for understanding the broader structure and evolution of galaxies. While they might seem like solitary wanderers lost in the cosmic void, their very existence, motion, and trajectories provide astronomers with unique insights into galactic dynamics, the distribution of mass, and even the elusive nature of dark matter. In a sense, these stars act as natural probes, carrying information about their home galaxies far beyond the regions we can observe directly. One of the most direct ways hypervelocity stars inform galactic evolution is through their trajectories. Because their motion is governed largely by gravity, tracing the paths of hypervelocity stars allows astronomers to map the gravitational potential of the Milky Way. By measuring their velocities, distances, and directions, scientists can infer the mass distribution of the galaxy, including contributions from stars, gas, and the invisible dark matter halo that envelops the Milky Way. A star traveling at extreme velocity is sensitive to even subtle variations in the galactic gravitational field, making it a natural experiment in motion. Deviations in its trajectory can indicate the presence of unseen mass or asymmetries in the galaxy structure. This leads directly to one of the most important applications of hypervelocity stars: probing dark matter. Dark matter does not emit, absorb, or reflect light, making it undetectable through traditional telescopes. Yet its gravitational influence shapes the motion of stars, gas, and entire galaxies. Hypervelocity stars, especially those ejected from the galactic center or from other violent events, move along paths that take them through regions dominated by dark matter. By carefully modeling how these stars travel through space, astronomers can estimate the density, distribution, and shape of the dark matter halo. Each hypervelocity star becomes a tracer particle, revealing the invisible scaffolding that holds galaxies together. Hypervelocity stars also provide insights into galactic morphology, the shape and structure of the galaxy. For instance, if stars ejected from the galactic center follow trajectories that are deflected or skewed in particular directions, This may indicate that the Milky Way's halo is not perfectly spherical, as often assumed, but oblate, triaxial, or irregular due to past mergers or interactions. These observations allow astronomers to refine models of the galaxy's shape and evolution, giving a more accurate picture of how the Milky Way and other galaxies have formed and changed over billions of years. Furthermore, hypervelocity stars help us understand stellar population dynamics and galactic history. By analyzing the chemical composition of these stars, astronomers can determine their birthplace, age, and original environment. For example, stars ejected from the galactic center often have unique chemical signatures that differ from those in the galactic disk or halo. This allows scientists to reconstruct the conditions near supermassive black holes, providing indirect evidence of past star formation, accretion events, and even mergers with other galaxies. Essentially, hypervelocity stars act as archaeological records, preserving information about regions of the galaxy that are otherwise difficult to observe directly. Additionally, the study of hypervelocity stars informs our understanding of galactic evolution through interactions and mergers. Some of these stars may have originated not within the Milky Way but in dwarf galaxies that were later absorbed. By identifying their unusual velocities and trajectories, astronomers can detect evidence of past mergers, interactions, and galactic cannibalism, helping reconstruct the Milky Way's dynamic history. Each hypervelocity star is, in a sense, a relic of cosmic violence, a survivor whose path through space tells the story of dramatic events shaping the galaxy. Hypervelocity stars also help quantify the efficiency of black hole ejections and dynamical interactions. By comparing the observed number of hypervelocity stars with theoretical predictions, scientists can estimate how frequently stars are expelled from galactic centers, how often binary breakups occur, and how effectively galaxy mergers can accelerate stars to escape velocity. This, in turn, helps refine models of galaxy formation and evolution, offering a window into processes that operate on scales far beyond human observation. Finally, hypervelocity stars remind us that galaxies are not static. The Milky Way, like all galaxies, is a dynamic, evolving system where stars are born, interact, and sometimes are violently ejected. These ejections play a subtle but significant role in redistributing mass and energy, influencing the galactic halo, and even potentially seeding intergalactic space with stars. Their motion, energy, and trajectories provide clues to the hidden mechanics of the universe, allowing astronomers to connect small-scale stellar events with the grand-scale evolution of galaxies over billions of years. In short, hypervelocity stars are more than curiosities. They are natural laboratories for studying the unseen and the extreme. By tracing their paths, measuring their velocities, and analyzing their chemical composition, astronomers can uncover the shape of galaxies, the distribution of dark matter, and the violent histories that shape them. Each star is a messenger, carrying critical information about the hidden mass, gravity, and dynamics that define our galaxy and the cosmos at large. Hypervelocity stars are not only probes of galactic structure and dark matter, they are also extraordinary windows into the extreme physics surrounding supermassive black holes, particularly those at the centers of galaxies. Because we cannot observe the immediate environment of these black holes directly at high resolution, hypervelocity stars provide a unique indirect method for understanding the violent gravitational dynamics that occur in their vicinity. Studying these stellar exiles allow astronomers to infer processes that would otherwise remain entirely hidden. The key connection lies in the mechanism of ejection. One of the primary ways hypervelocity stars are launched at speeds sufficient to escape the galaxy is through close interactions with a supermassive black hole. Typically, this involves a binary star system wandering too close to the black hole's intense gravitational field. As discussed earlier, one star can be captured or consumed by the black hole, while the other is flung outward at tremendous velocity. By observing the ejection velocity, trajectory, and composition of hypervelocity stars, astronomers can reconstruct the characteristics of the black hole encounter, providing insights into the black hole's mass, gravitational influence, and immediate environment.
For instance, the velocity of an ejected hypervelocity star carries a direct imprint of the black hole's mass. A more massive black hole exerts a stronger gravitational pull, allowing it to impart greater energy to a star during a slingshot interaction. By measuring hypervelocity stars like S5HVS1, which moves at around 1700 kilometers per second, scientists can infer that such extreme velocities are consistent with a close encounter with Sagittarius A, the supermassive black hole at the Milky Way center, which contains roughly 4 million solar masses. The observed speeds validate theoretical predictions of stellar dynamics in the intense gravitational field near a supermassive black hole. Beyond velocity, the trajectories of hypervelocity stars provide information about the geometry of the black hole environment. Stars ejected nearly radially from the galactic center indicate that the interaction occurred very close to the black hole itself. Deviations from purely radial paths can hint at additional influences, such as the presence of other stars, stellar clusters, or even secondary black holes. In this way, hypervelocity stars serve as natural tracers of the complex gravitational interactions near galactic nuclei, revealing the otherwise invisible choreography of stars in extreme conditions. Hypervelocity stars also offer clues about binary star populations near black holes. Because many hypervelocity stars originate from disrupted binaries, studying their properties allows astronomers to infer the frequency, mass distribution, and orbital parameters of stars that dwell in the black hole's vicinity. For example, if most hypervelocity stars are relatively massive, it suggests that the black hole preferentially interacts with certain types of binaries, or that massive binaries are more likely to survive close encounters long enough to be ejected. This information helps scientists refine models of stellar populations near galactic centers and understand how black holes influence their surrounding stellar environment. In some cases, hypervelocity stars can even provide indirect evidence of dormant or secondary black holes. If a star's trajectory cannot be fully explained by the central black hole alone, it may suggest gravitational perturbations from an unseen companion black hole, perhaps a remnant of a past galactic merger. By mapping hypervelocity stars with unusual paths, astronomers can infer the existence of these massive unseen objects, offering insights into the dynamics of galactic nuclei that are otherwise impossible to observe directly. Moreover, the chemical composition of hypervelocity stars offer additional clues. Stars ejected from near the galactic center often carry signatures of their birth environment, which is typically rich in metals and influenced by intense radiation fields. Comparing these compositions with stars in the galactic disk or halo allows scientists to pinpoint the star's origin and verify that it indeed originated in regions dominated by a supermassive black hole. This cross-analysis of motion and chemical fingerprinting strengthens the connection between hypervelocity stars and black hole interactions.
Hypervelocity stars also provide insights into galactic morphology, the shape and structure of the galaxy. For instance, if stars ejected from the galactic center follow trajectories that are deflected or skewed in particular directions, this may indicate that the Milky Way's halo is not perfectly spherical, as often assumed, but oblate, triaxial, or irregular due to past mergers or interactions. These observations allow astronomers to refine models of the galaxy's shape and evolution, giving a more accurate picture of how the Milky Way and other galaxies have formed and changed over billions of years. Furthermore, hypervelocity stars help us understand stellar population dynamics and galactic history. By analyzing the chemical composition of these stars, astronomers can determine their birthplace, age, and original environment. For example, stars ejected from the galactic center often have unique chemical signatures that differ from those in the galactic disk or halo. This allows scientists to reconstruct the conditions near supermassive black holes, providing indirect evidence of past star formation, accretion events, and even mergers with other galaxies. Essentially, hypervelocity stars act as archaeological records, preserving information about regions of the galaxy that are otherwise difficult to observe directly. Additionally, the study of hypervelocity stars informs our understanding of galactic evolution through interactions and mergers. Some of these stars may have originated not within the Milky Way, but
but in dwarf galaxies that were later absorbed. By identifying their unusual velocities and trajectories, astronomers can detect evidence of past mergers, interactions, and galactic cannibalism, helping reconstruct the Milky Way's dynamic history. Each hypervelocity star is, in a sense, a relic of cosmic violence, a survivor whose path through space tells a story of dramatic events shaping the galaxy. Hypervelocity stars also help quantify the efficiency of black hole ejections and dynamical interactions. By comparing the observed number of hypervelocity stars with theoretical predictions, scientists can estimate how frequently stars are expelled from galactic centers, how often binary breakups occur, and how effectively galaxy mergers can accelerate stars to escape velocity. This, in turn, helps refine models of galaxy formation and evolution, offering a window into processes that operate on scales far beyond human observation. Finally, hypervelocity stars remind us that galaxies are not static. The Milky Way, like all galaxies, is a dynamic, evolving system where stars are born, interact, and sometimes are violently ejected. These ejections play a subtle but significant role in redistributing mass and energy, influencing the galactic halo, and even potentially seeding intergalactic space with stars. Their motion, energy, and trajectories provide clues to the hidden mechanics of the universe, allowing astronomers to connect small-scale stellar events with the grand-scale evolution of galaxies over billions of years. In short, hypervelocity stars are more than curiosities. They are natural laboratories for studying the unseen and the extreme. By tracing their paths, measuring their velocities, and analyzing their chemical composition, astronomers can uncover the shape of galaxies, the distribution of dark matter, and the violent histories that shape them. Each star is, in a sense, a relic of cosmic violence, a survivor whose path through space tells a story of dramatic events shaping the galaxy. Hypervelocity stars are not only probes of galactic structure and dark matter, they are also extraordinary windows into the extreme physics surrounding supermassive black holes, particularly those at the centers of galaxies. Because we cannot observe the immediate environment of these black holes directly at high resolution, hypervelocity stars provide a unique indirect method for understanding the violent gravitational dynamics that occur in their vicinity. Studying these stellar exiles allows astronomers to infer processes that would otherwise remain entirely hidden. The key connection lies in the mechanism of ejection. One of the primary ways hypervelocity stars are launched at speeds sufficient to escape the galaxy is through close interactions with a supermassive black hole. Typically, this involves a binary star system wandering too close to the black hole's intense gravitational field. As discussed earlier, one star can be captured or consumed by the black hole, while the other is flung outward at tremendous velocity. By observing the ejection velocity, trajectory, and composition of hypervelocity stars, astronomers can reconstruct the characteristics of the black hole encounter, providing insights into the black hole's mass, gravitational influence, and immediate environment. For instance, the velocity of an ejected hypervelocity star carries a direct imprint of the black hole's mass. A more massive black hole exerts a stronger gravitational pull, allowing it to impart greater energy to a star during a slingshot interaction. By measuring hypervelocity stars like S5HVS1, which moves at around 1700 kilometers per second, scientists can infer that such extreme velocities are consistent with the close encounter with Sagittarius A, the supermassive black hole at the Milky Way center, which contains roughly 4 million solar masses. The observed speeds validate theoretical predictions of stellar dynamics in the intense gravitational field near a supermassive black hole. Beyond velocity, the trajectories of hypervelocity stars provide information about the geometry of the black hole environment. Stars ejected nearly radially from the galactic center indicate that the interaction occurred very close to the black hole itself. Deviations from purely radial paths can hint at additional influences, such as the presence of other stars, stellar clusters, or even secondary black holes. In this way, hypervelocity stars serve as natural tracers of the complex gravitational interactions near galactic nuclei, revealing the otherwise invisible choreography of stars in extreme conditions. Hypervelocity stars also offer clues about binary star populations near black holes. Because many hypervelocity stars originate from disrupted binaries, studying their properties allows astronomers to infer the frequency, mass distribution, and orbital parameters of stars that dwell in the black hole's vicinity. For example, if most hypervelocity stars are relatively massive, it suggests that the black hole preferentially interacts with certain types of binaries, or that massive binaries are more likely to survive close encounters long enough to be ejected. This information helps scientists refine models of stellar populations near galaxy centers and understand how black holes influence their surrounding stellar environment. In some cases, hypervelocity stars can even provide indirect evidence of dormant or secondary black holes. If a star's trajectory cannot be fully explained by the central black hole alone, it may suggest gravitational perturbations from an unseen massive companion, black hole, perhaps a remnant of a past galaxy merger. By mapping hypervelocity stars with unusual paths, astronomers can infer the existence of these massive hidden objects, offering insights into the dynamics of galactic nuclei that are otherwise impossible to observe directly. Moreover, the chemical composition of hypervelocity stars offers additional clues. Stars ejected from near the galactic center often carry signatures of their birth environment, which is typically rich in metals and influenced by intense radiation fields. Comparing these compositions with stars in the galactic disk, or halo, allows scientists to pinpoint the star's origin and verify that it indeed originated in regions dominated by a supermassive black hole. This cross-analysis of motion and chemical fingerprinting strengthens the connection between hypervelocity stars and black hole interactions.
The distances involved also underscore the isolation of these stars. While planets, asteroids, and even interstellar clouds orbit and interact within a galaxy, hypervelocity stars travel through regions where encounters are so rare that they may pass near no other matter at all for millions of years. Their interactions with gas or dust in the intergalactic medium are minimal, meaning they essentially coast through the void at incredible speeds. Even if they were to emit light continuously, their faint glow would be nearly impossible to detect from such extreme distances, emphasizing both their loneliness and the enormity of the universe they traverse. This cosmic scale also magnifies the energy they carry. Traversing millions of light years at velocities exceeding 1,000 kilometers per second is not just a journey of distance, but a testament to the extreme forces that propelled them. Their motion encodes information about gravitational interactions near supermassive black holes, galaxy collisions, and binary star disruptions, all of which occurred billions of years ago. In this way, hypervelocity stars are both travelers and historical records, carrying the imprint of cosmic events across incomprehensible expanses. Furthermore, considering hypervelocity stars on a cosmic scale reinforces the interconnectedness of galaxies. While each star originates in a particular galaxy, its journey can bridge enormous distances, potentially passing near or even through other galaxies over time. Though captured by another galaxy is rare, these stars highlight the permeability of cosmic boundaries. Even the vast emptiness between galaxies is not entirely empty, and stars can traverse these voids, connecting different regions of the universe in subtle but meaningful ways. Ultimately, the scale of hypervelocity stars forces us to confront the sheer vastness and dynamism of the cosmos. They are not merely fast stars. They are exiles, traveling distances that dwarf our entire galaxy, drifting through space for billions of years with no destination and no companions. Their existence reminds us that the universe is not static. It is dynamic, violent, and full of interconnected in ways that challenge our imagination. Hypervelocity stars are the ultimate cosmic travelers, galactic refugees carrying with them the history, energy, and secrets of the galaxies that launched them. As we reflect on the incredible journey of hypervelocity stars, from their violent ejection near supermassive black holes, to their solitary drift across intergalactic space, to the extreme energies they carry, it becomes clear that these stars are far more than astronomical curiosities.
They are symbols of the universe's raw power, its unpredictability, and its boundless scale. Unlike the stars we see twinkling in familiar constellations, hypervelocity stars are not content to remain tethered to their homes. They defy the gravitational chains of galaxies and embark on odysseys that span millions of light years, carrying with them the history of extreme cosmic events. Every hypervelocity star tells a story. Some were violently ejected from the galactic center, slingshotted by the immense gravity of a supermassive black hole. Others were torn from their binary partners or accelerated during dramatic galaxy collisions. Each one represents a violent event so powerful that it can catapult a massive star out of its galactic cradle and into the vast darkness of intergalactic space. They are survivors of forces that dwarf human imagination, carriers of kinetic energy so immense that they could destabilize planetary systems or stir distant molecular clouds. Yet, despite their power, hypervelocity stars are profoundly lonely. Once ejected, they drift in isolation for billions of years, invisible to most telescopes and largely disconnected from the galactic life they once knew. They are stellar exiles and cosmic messengers, preserving clues about the structure of galaxies, the distribution of dark matter, and the extreme physics surrounding black holes. Observing them challenges astronomers to refine their instruments, push the limits of detection, and rethink what it means for a star to wander freely through the universe. Hypervelocity stars also expand our understanding of scale. The distances they traverse, the energies they carry, and the time spans over which they travel make them almost incomprehensible. They move across millions of light years, surviving in isolation, yet still encoding information about their violent origins. They remind us that the universe is not static, it is dynamic, violent, and full of cosmic wanderers racing through the void. Every hypervelocity star is a testament to the forces that shape galaxies, the power of gravity, and the extraordinary extremes of astrophysical phenomena. They are cosmic reminders that even the most massive, seemingly stable objects can be thrown into motion, crossing the universe with a momentum that outlasts civilizations, histories, and even the stars themselves. In observing and studying these stellar fugitives, we glimpse the universe as it truly is, a place of motion, energy, and unpredictability, where every object, no matter how massive, is subject to the cosmic dance of forces that sculpt the cosmos. Hypervelocity stars are not merely fast-moving stars. They are emissaries of cosmic violence and endurance, racing endlessly through the void, carrying with them both the secrets of their past and the awe-inspiring testament to the universe's dynamic nature. Hypervelocity stars are reminders that the universe is not static, it's dynamic, violent, and full of cosmic wanderers racing through the void. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.